Yeah, all right. So hello everyone again. My today's talk is gonna be a different flavor from what you've been hearing from me past week and this week as well. Today I'm gonna be talking about how to probe cosmology as well as baryonic feedback using FRBs. So Pawan has already highlighted some of the aspects of how to do cosmology with FRBs and how to use them as probes. And I'm gonna focus on DMC analysis and cross correlations for FRBs. So firstly, a quick review of what is the matter power spectrum, because you'll hear a lot about matter power spectrum suppression from me in this talk. So the matter power spectrum is basically, it just quantifies how density fluctuations are distributed across different spatial scales. So if you think of all matter over densities being denoted by delta M, then the matter autocorrelation function, usually denoted by xi of R, is an average over all spatial realizations of matter over density separated by a distance of R. And if you take a Fourier transform of this, which I'm sure all of you are expert of here, what you get is the Fourier representation of the matter autocorrelation function or the matter power spectrum. Theoretically, if you were to assume that all the matter in the universe is in halos of a certain size, then you would expect this matter power spectrum to have some contribution from clustering of halos at large scales, which is usually coined as this two halo term. So you can imagine these blue circles as denoting halos, then you will have contribution from clustering at large scales. And then you would also expect to have some contribution from clustering within the halos, which is the one halo term. And if you write the matter power spectrum, it should basically just be a linear sum of one halo and two halo terms. And more specifically, if you think of it in Fourier space, again, for the matter power spectrum, then at large scales or small k values, you expect the two halo term to dominate. And at small scales or large k values, you expect the one halo term to dominate. So for feedback, you would expect that your feedback should impact the matter power spectrum at these small scales where the mass is being pushed out of the halos. So let's again imagine this particular halo of size R halo, and once feedback kicks in, it pushes out matter out to larger radii, let's say out to R ejected radius. Then mathematically, you can write as the change in your matter over density delta prime by delta as being approximately 1 minus the ejected mass over the halo mass, where your ejected mass is nothing but the baryon fraction in the universe, omega b by omega m, minus the baryon fraction in this leftover halo. So given this simple mathematical formalism, order of magnitude, you can write the expected change or the suppression in matter power spectrum to be approximately proportional to this baryon fraction in a given mass halo. So the idea is that your baryon fraction in a given mass halo, which is also being traced by FRBs, is correlated with the suppression of matter power spectrum, which is also of interest to all the cosmologists out there. So more specifically, if you basically look at your matter power spectrum again, but if your scales are larger than, if the scales that you are measuring the matter power spectrum at are larger than the characteristic size of your halo, then you don't really expect to have any impact from baryonic feedback, and your suppression or P hydro by pre-gravity only is approximately 0, or the ratio is basically 1. But as you start moving towards smaller scales, your feedback kicks in, it pushes out baryons out to larger radii, and you basically lose power at these intermediate scales of around 1 to 0.1 megaparsec inverse. Further, as you go to even smaller scales, at some point, star formation starts to dominate and your power in the power spectrum again increases. So there's significant interest in cosmological community to basically put constraints on the suppression of matter power spectrum, because all your upcoming weak lensing surveys are interested in conducting precision measurements of matter power spectrum, and these are all these effects can be on the scales of 1 to 10% depending on which scale you're looking at. So in this really nice work led by Leah Bigwood, who works with Alex Amon and Princeton, they took cosmic shear data from DES year 3 and analyzed data using 3 methods for how they model baryonic feedback within the matter power spectrum formulation. So for example, in this one, they're using the baryon here they're using the baryon fraction in a given mass halo. And you can see how S8 positively correlates with the baryon fraction in that halo. Similarly, if you use any other method where, let's say, your feedback is parameterized by either TAGN or any other formalism for feedback, you would observe that your feedback parameters are basically degenerate with cosmology. So all this tussle around what is this SA tension, can it be explained by feedback? The answer is probably yes. We don't fully understand how to model feedback really. And if you look at SA tension really, so here the bottom point is for Planck measurement. And if you don't use any baryon mitigation techniques in cosmic shear or weak lensing analysis, then this is your expected measurement. And this basically is your observed SA tension, where you can see that this is like order 1 to 2 sigma result, that there is some tension. But then again, depending on how you model your feedback in terms of your matter power spectrum, you could basically be all over the place. So if instead of modeling feedback through such halo model approaches, if there's some probe that you can use to just put constraints on feedback and use that data directly, that would be very, very useful. An example of this, again by Leia, was where she combined data from cosmic shear with that of weak lensing. And in such cases, you can clearly see how your constraints on power spectrum suppressions greatly improve. And there are several other works which have tried to combine cosmic shear or weak lensing with TSZ or X-ray observations. All of these are probes of baryons, and they probe baryons at different halo mass scales. So if you can combine cosmic shear with other probes of gas distribution, you can constrain feedback directly, and it would basically help you break the degeneracy between cosmology and astrophysical feedback. I think we've heard a lot about this already, but we know that FRB dispersion measures probe baryons, where DMs are nothing but just a line of sight integral of electron density. So you can think of an example FRB burst propagating through, let's say, elasticity in G universe. As the burst propagates through the universe, your DM increases with distance. And as soon as it crosses this massive halo along the line of sight, you observe this huge bump in dispersion measure of order of hundreds or thousands of DMs. So the basic idea behind using FRBs as probes of cosmology is to find multiple FRBs in multiple sight lines out to different redshifts, and basically use the distribution of FRBs in D and Z space to put constraints on cosmology as well as feedback. So if you look at the FRB sight line, beginning from the FRB location, you expect to have some contribution from the host galaxy. Then majority contribution, depending on your redshift of the FRB, could be from the IGM or the intervening halos. And finally, there is some contribution from our own Milky Way galaxy halo, as well as its ISM. So there are ways of modeling the Milky Way ISM contribution based on our understanding of pulsars in our own galaxy. And for galactic halo also, we know that it's order 50 to 80 parsecs per cc. But we poorly understand this combination of host and cosmic DM, and the observable of primary interest is this cosmic DM. So DM host ends up being degenerate with your primary observable of interest. So we need to have some way of modeling this. So if you come back to the FRB DM redshift relation, so again, we've already seen this plot multiple times during this conference. So this one is by Liam Connor's work, where we took a sample of about 70 FRBs to put constraints on fraction of baryons in IGM as well as CGM. So for any example DMZ relation, the first observable would be the mean of the relation. So the mean of this relation should only depend on the mean baryon density in the universe and cosmology. So once you plug everything in, you can see that it explicitly depends on cosmological parameters like H0 weighted by baryon density in the universe, as well as matter density parameter and omega lambda. So I think one of the most recent constraints on cosmological parameters using FRBs goes down to as good as 10% for H0. The second observable, which is of primary interest to me specifically, is the variance or the spread in the DMZ relation. So I discussed this yesterday as well. So here I'm showing 3 different hydrosimulations: Astrid, Elasticity NG, and Simba. Each of them have different underlying feedback physics implementation. Going from Astrid to Simba, you have stronger feedback strength. So you can see how the halos are devoid of baryons in case of Simba. And as you proceed towards Astrid, the halos are more clumpy. The expected impact on observed DMC relation is that in case of weak feedback scenarios, like in case of Astrid, you have larger spread in DMZ relation. And as you increase the feedback strength, the spread in the relation actually reduces. Mathematically, this is because your variance in dispersion measure is explicitly dependent on the electron autocorrelation function, which is just an inverse Fourier transform of the electron power spectrum. So the variance in this relation depends on degree of clustering of baryons at different scales. Just to put FRBs in the broader context of all probes of baryons, so first of all, we have X-ray observations, which are sensitive to the most massive halos out there. The sensitivity goes as m to the power 7/3. So the sensitivity peaks somewhere around 10^15 Empson halos. Next, we have thermal SZ effect, where the sensitivity goes as m to the power 5/3 and is sensitive to relatively lower mass halos. Next, we have KSZ effect, which it's difficult to evaluate the sensitivity directly in terms of halo masses because it's proportional to the peculiar velocity distribution of this field as well. But based on existing observations from ACT LRG stacks, it seems to peak somewhere around 10^13 Ensign halos. Cosmic shear, which is the ultimate goal for upcoming surveys like Euclid. The idea again is to measure the matter power spectrum to infinite precision. The halo mass sensitivities all the way from 10^10 Empson halos to 10^16 Empson halos. So these three probes alone are not sufficient for us to be able to comment on what's going on with baryons in this broad halo mass regime. So coming back to FRBs, with beam dispersion measure, we should technically be sensitive to these lower mass halos. Again, that is dependent on your baryon fraction in those halos as well. So this could technically go down something like this, but it depends on feedback. The variance or the spread in the DMZ relation, on the other hand, peaks somewhere around 10^14 Empson halos and is quite complementary to all these other probes of baryons as well. So developing FRBs as a probe of baryons is not only essential to put constraints on suppression of matter power spectrum, it also adds to this broader spectrum of our now knowledge of distribution of baryons. In one of our recent works, which is what I wanted to present today, we used 1,000 variations of elasticity in G within the CAMELS project to look at correlations of variance in FRB dispersion measure as a function of redshift and the suppression of matter power spectrum across different scales. So here you can think of color as denoting the strength of baryonic feedback, where blue represents weak feedback and hence larger variance, and white or this green color denotes strong feedback scenario or smaller variance. So you can see that there's an approximately 1-to-1 correlation between variance in DM as a function of redshift and suppression of matter power spectrum. So if we can actually measure this, then we should directly be able to translate that measurement into a suppression measurement as well. We went ahead and did some forecasts, especially for upcoming surveys like DSA 2000, where we'll have 10^4 FRBs populating the DMZ space. The expected constraints are about 1% precision on large scales of about a megaparsec inverse, and about 10% precision at relatively smaller scales of 10 megaparsec inverse. And this is not just about constraining the suppression of matter power spectrum. You can also translate that measurement into a baryon fraction of different mass halos. So if you recall in one of the first slides, it's shown how suppression of matter power spectrum correlates with baryon fraction in halos. So if you have that measurement, you can translate it to gas profiles or baryon fractions in different halos under halo models. So as an example here, I'm showing the correlation coefficient as a function of scales for different mass halos. So you can see that the suppression at different scales correlates with different halo masses. And this is a well-known approach where folks have used this to put constraints on baryon fraction in galaxy groups and clusters using X-ray data, which is basically independent of the actual X-ray data. So you can basically compare the two and see if there's any tension in measurements from different probes. Finally, in the last couple of minutes, I would like to highlight that within the FRB community, there's an increasing interest to conduct statistical DM galaxy cross correlations. So DM galaxy, so dispersion measures when cross correlated with galaxies are expected to have a positive correlation because, of course, baryons are sitting around galaxies themselves. And if you mathematically look at the expected observable, it depends on the galaxy electron cross power spectrum this time. So this formalism is very similar to any other cross correlation that you hear about of galaxy-galaxy autocorrelations, galaxy matter cross correlations, and so on. So here are some expected forecasts with 10 power 4 FRBs again. Specifically, I would like to highlight this corner plot of S8 versus omega B. So there's this strong degeneracy in DM-DM autocorrelation and DM-galaxy cross correlations. So that means once you add in multiple probes to it, which lead to even slight rotations in this particular ellipse, you should be able to start breaking down these degeneracies in multiple parameters. I would also like to highlight that first detections of such statistical cross correlations are already coming in. For example, this one by Mariam Hussaini looked at correlations of excess galaxy number densities for FRB sight lines. And we already find an approximately 2 to 3 sigma detection of an excess DM along FRB sight lines with excess galaxy number densities. Recently by CHIME, using a sample of about 3,000 FRBs, when cross-correlating with galaxy surveys, they've already found a 5 sigma detection of such cross-correlation signals. So the future of this thing looks really bright. We need to just continue building on larger FRB samples so that we could start giving meaningful contributions to this cross-correlations that are performed by all the cosmologists across the world. Again, I would say the future looks really bright. There are multiple surveys which are continuing to build larger FRB samples. We are already at a sample of around 120 FRBs with known host galaxies and spectroscopic redshifts. So we should continue pushing in this direction and building larger and larger FRB samples so we can start doing precision cosmology. With that, I think I might be running out of time, so I'm just going to leave my summary slide up here and take any questions. Thank you so much.
Thank you, Kritti. Questions for Kritti? Yeah, yes, please. Go ahead.
One complication that comes into this analysis, which is very impressive, by the way, would be that DM host could evolve with redshift, with galaxy properties, and so on. And to understand that, there are some ways to try and infer that retrospectively from observations. We did one work on this recently, but from the simulation side, one would really need zoom-in cosmological simulations. And I was wondering if you're going to implement that into this kind of analysis, looking into all these properties that you mentioned.
Yeah, that's an excellent question. So especially for DMZ analysis, I'm still working on understanding what the expected impact could be if there was indeed a redshift evolution of host DM. So that is still ongoing work. But at least for cross correlations, I would like to highlight that when we do such cross correlations, we are looking for signals in foreground of FRBs. So we are looking for excess foreground DM that cross correlates with excess galaxy number density along the sight line. So in that case, the FRB host DM is probably not as big of a problem. However, we do need to account for it in the covariance matrix when you actually conduct or write the observed likelihood. And in there, you could add in host redshift evolution if you want to, or you can basically boost up your host DM variance just to account for such uncertainties. So we are still thinking more about how we can model such host DM uncertainties and what sample size would these effects start to become a problem.
More question for Kritti? Yeah, maybe I can ask one. So you talked about excess DM in the direction of FRBs in the galaxies. So can that have some implication on choosing the targets where to search for FRBs?
Do you mean choosing the fields?
Choosing the fields.
Yeah, so I mean, ideally, we would want to be looking in fields where we already have good galaxy maps with spectroscopic redshifts. And for example, in case of DSA 2000, the plan is to have larger number of epochs or better observing depth at fields that are covered by Euclid. So that basically helps because, I mean, galaxies are randomly distributed, but having spectroscopic redshifts available from some other surveys is always useful. So we are trying to have overlap with Euclid, at least in case of DSA 2000, for example.
Yeah, more questions and also questions from online participants. Do you have any questions? Please unmute yourself and ask.
Yeah, so can you hear me?
Yeah, we can hear you.
Yes.
Yeah, so maybe this was discussed in some other talks or will be discussed. So has the missing baryon problem been got solved because of FRBs? Because of FRB observations?
That's a very controversial question to ask. So, for example, I mean, in McQuarrie paper, we do claim that we solved the missing baryons problem by claiming that there's a one-to-one correlation between DM and redshift. But I mean, to really solve the missing baryon problem, I think we need to have some constraints on baryon fraction and IgM versus halos. And I think there's like already ongoing amazing work from flim-flam surveys, for example, where they're building on larger samples to put constraints on FIGM and FCGM. So missing baryon problem is all about asking what is the fraction of baryons that is sitting within the halos versus what is diffuse or in the IgM. So I would say it's still ongoing work and FRBs can help solve that problem sometime soon.
More questions? Okay, if not, let us thank Kritti.